Okay, so welcome back. This is going to be part 2 of section 8.4. And I think I fixed that clicking noise that kept getting recorded when I would tap my pen on the screen. So hopefully it'll be a little better. I might be a little bit muffled. I'll try to speak up. But here we go. We're in binomial probabilities, and we're looking at this problem right here on the screen. And it reads, a survey of consumer finance found that 25.4% of credit card holding families hardly ever pay off the balance. Suppose a random sample of 20 credit card holding families is taken. Find the probability of each of the following results. Exactly 6 families hardly ever pay off the balance. Exactly 9 families, exactly 4. At least 4 and at most 5. Okay. All right, so I read a whole bunch in here, and I'm thinking it's binomial, mostly because I'm in the binomial section, but I think it's binomial for other reasons too. Because it looks like we're doing the same thing a bunch of times. That is, we are knocking on 20 doors, and we are asking them the question, do you ever pay off your balance? Okay? We are defining success to be them saying that they don't pay it off. So that's our definition of success. That probability of success is going to be 0.254. Okay? That's that 25.4% from up there. Okay? Let's see, what else we got here? Let's see. I think, if I remember correctly, for the calculator, the only things I need are the n, the p, and the x. So I think I can jump in and start looking at some of these questions. All right, so I'll take a look at the first one. Exactly 6 families hardly ever pay off the balance. That means, using all of this over here, I want to find the probability that x is exactly 6. Now I could use that formula, but if you've learned nothing about me, I hope that you've learned that I'm lazy and I like to use technology when I can. So I am going to use that binomial PDF, and I know that it's the binomial PDF one. The PDF because I just want one value for my random variable. So I'm going to go back to that distribution menu. I'm going to find that binomial PDF, and I'm going to say, okay, we're knocking on 20 doors. The probability that they will not pay off their credit card is 0.254, and I want there to be exactly 6 of the 24 that say that, and I find that that gives me a probability of 17%, or round wherever they would tell me to round it to. So I'm going to call that 0.172. So I've got about a 17% chance that if I go knock on 20 doors, 6 of those people will say, nope, we don't pay it off. Right? All right. How is that different from the second question here, where it says exactly 9 families hardly ever pay it off? Well, that just means this. Probably that the random variable is equal to 9. In fact, I can just go back into that same command, and the only thing I need to change is that 6 needs to change into a 9, because there's still 20. So that's still 20. There's still 0.254 probability of success. And so I get a, wow, that dropped significantly. Now I'm down to a 0.029% chance. So by increasing by 3 people, I lost a bunch of percent. I lost 15% chance. Well, this isn't too bad. So once I can identify that something is binomial, I'm looking for an n, a p, and then whatever x value the problem gives me. And I'm just plugging it into the binomial PDF because it wants a specific x value. All right, let's look at the next one. The next one reads, what does the next one read? The next one reads, at least 4 families hardly ever pay off their balance. Okay, this one's going to be tricky. So luckily, I saved us a bunch of space. Okay, what does at least 4 mean? Okay. At least 4 means the smallest number we'll accept is 4, but we'll accept bigger numbers. So that means that it could be 4, or it could be 5, or it could be 6, or 7, or, all the way up to 20. Can't go higher than 20 because we're only surveying 20 people. I got a problem. Here's my problem. The Binomial Cdf command, the one that's built into my calculator, the one that I used last time, the CDF version, that does a left tail. That does 0 and 1 and 2 and ... and stops wherever you tell it to stop. That's the left half of this, and our problem wants us to find the right half of this. So how am I going to do this? Well, I'm going to use something we've talked about many times before, the complement. The probability that x is greater than or equal to 4 is just going to be 1 minus the probability that x is less than or equal to 3. All right? So what I'm going to do is I'm going to make the following argument. The probability of 1 or 2 or 3 or ... all the way up to 20 has to add up to 1. All of them add up to 1. So if I did 1, 2, 3, plus the probability of 4, 5, 6, 7, 20, that adds up to 1. And if I want this piece, I'm just going to take that piece and move it to the other side. And when I move that piece to the other side, that's where I get this statement right here. The probability that x is 4 or more is just 1 minus the probability that x is 3 or less. So then I'm going to go grab my calculator and I'm going to calculate that out. That's going to be 1 minus, let's see, clear that mask, go to my distribution menu, Binomial CDF, 20 trials, probability of success is 0.254. The x value is 3, because that's the highest one I want to calculate. And I get 0.213. 24, wherever they tell me to round it. So 1 minus that answer. And I get that this works out to be, again, round it wherever they tell me to round it, 787. We have roughly a 79% chance that this is going to happen. Okay. Last one. At most 5 families never pay off their credit card debt. So what does at most 5 look like? Well, at most 5, that means 0 or 1 or 2 or 3 or 4 or 5. In fact, that's the left half that we want. Oh, that doesn't look good at all when I use the pink on top of the pink. That was a 2, that's a 3. So let's use yellow on top of pink. Okay? That's just the Binomial CDF command. So I'm just going to say that's going to be the probability that x is less than or equal to 5. So come over to the calculator, distribution, CDF command, because I want from 0 all the way up to 5, still 20 trials, still 0.254, but now I want it up to 5, and I get a 60%, 0.601, so 60.1% chance. So this is binomial probability. Calculating binomial probabilities isn't that hard, because you got a calculator that does most of the work for us. There are 3 different versions of the problem. Okay? There's this version, the first 2 examples here, which are binomial PDF. We just want a specific value. We just plug it in, x is exactly a number, grind it out, we're done. Then there's these 2 problems. Okay? And I think of these as left tail problems or right tail problems. Right? Binomials always go from 0 up to some fixed number from the problem. So in this case, they went from 0 on the low end up to 20. The tail problems, the left tail, right tail problems, always give you somewhere in the middle to split it. In the first example, let's split it at 4. And so then this would be the left tail in my language. This would be the right tail in my language. Okay? Left tails are always the CDF. And right tails are always 1 minus the left tail. So we always turn right tail problems into left tail problems and grind them out that way. Okay? And those are the 4 types of problems. Once you identify it as binomial, figure out which one it is and grind it out. Okay? Let's take a look at this next example, color blindness. The probability that a male will be colorblind is 0.042. Okay? So there's my probability of color blindness. Find the probability that in a group of 53 men, so there's my sample size, 53 men, the following will be true. Exactly 5 will be colorblind. Right? All right, so first things first, I go back to the beginning. Is this binomial? Am I doing the same thing over and over again? Well, it looks like I'm walking up to 53 men and I'm saying, are you colorblind? The answers are yes or no, 2 options. We're defining success to be colorblind, so yes, it is binomial. Success is that you're, I'm just going to use CB for colorblind. The probability of success is 0.042. Right? And then I just have to calculate some probabilities. I know that N is going to be 53 because I'm talking to 53 people. But in each of these examples, I need to figure out what I'm doing. All right, so in part A, that's an exactly 5. So that's a PDF problem. In part B, it's no more than 5. So that's 5 or less. So that's a CDF problem. That's the left side or the left tail problem. And then the last one says at least 1. So that's a CDF, but that's a right problem because at least means 1 or more. So now that I've got them figured out what they are, let's go calculate them. A is the probability that the random variable x is exactly 5. Well, calculator, clear, distributions, binomial PDF, because it's exactly 5. There are 53 trials of this experiment. Our probability for success is 0.042, 4.2%, and we want the x to be exactly 5. And that works out to be about whoa, what happened there? 0.048. Well, that's not too bad. I can do this. All right. Question 47, part B. No more than 5. No more than 5 means I want the probability that x is less than or equal to 5. So that's going to be the CDF because I'm doing the left hand on this one. So I've been back to my distributions. I'm looking for binomial CDF. Right? There's still 53 trials. Probability of success is still 0.042. My probability that I want is 5 for my maximum x value. And then I paste that back in. And I get, whoa, 0.977. So almost guaranteed there'll be 5 or less in a group of 53. I know it's not guaranteed because it's not 100%, but that's pretty close. I'm looking at almost a 98% chance. That's pretty high. All right, and then the last one is, oops, not B again, silly. Part C. I want to find the probability that x is greater than or equal to 1. At least 1. Right? I can't do that, so I'm going to do 1 minus the probability that x is 0. Because the only thing that is smaller than 1 is 0 in a binomial. And remember, what does a 0 mean here? A 0 means that of the 53 men, none of them are colorblind. So that is a viable or a valid option. Right? But because that's just the single value, I'm just going to use the PDF command to find that. So back to my distribution menu, PDF, 53 people I'm talking to, 0.042 probability of success. I want no successes, and so I get about a 10% chance. So it's 1 minus 0.103, and so then 1 minus that value. And I get that this is approximately 0.897, rounded to 3 decimal places. So there's about a 90% chance of having one or more colorblind men if you have a group of 53 men. All right, moving on to our last example, and then we'll be done with section 8.4. According to this doctor, Dr. Peter A.G.M. de Smet of the Netherlands, if an herb caused an adverse reaction in 1 in 1,000 users, a traditional healer would have to treat 4,800 patients with that herb to have a 95% chance of observing the reaction in more than one user. Verify this calculation by finding the probability of observing more than one reaction in 4,800 patients. Okay, so I'm seeing binomial. I hope at this point you are too. Okay? Binomial. And why is this binomial? Well, because I'm doing the same thing over and over again. So I am a traditional healer, not really, but for the purposes of this example I am. And I have a new patient coming in. I have one new patient coming in every single working day for more than 18 years. And I am going to administer this herb to them. Okay? So I'm knocking on 4,800 doors. I have a probability of seeing an adverse reaction of 1 out of 1,000. Okay? And I want to find out what is the probability that I will see a reaction in more than one user. So I want x to be greater than or equal to 1. Oh, wait a second. No, I don't. What does it mean to say more than one user? Well, more than one user means 2 or more. Whew, man, that slippery language almost got me. So that's what I want. Okay. Uh-oh. That's a right tail problem. So what I'm going to have to do is I'm going to have to convert that to a left tail problem. So I'm going to have to say the probability that x is greater than or equal to 2 is 1 minus the probability that x is less than or equal to 1. This is going to be that CDF command. Okay? So I'm going to go over to my calculator. I'm going to go to my distribution menu. I'm going to find that binomial CDF. I'm doing 4,800 trials. That's 4,800 patients. I have a probability of seeing an adverse reaction of 1 out of 1,000. I only want to see it at most one time. I get 0.47, right? So this is going to be 1 minus 0.047 and change. 47 rounded wherever they tell me to round it. So 1 minus that value. And I get 0.952 rounded, which is approximately 95.2%. So what does this mean? Well, what does it say? It said that we have something, we're giving an herb, a medicine of some sort, and it has a chance of having an adverse reaction of 1 out of 1,000. it would take me 4,800 times to give people that drug before I would be mathematically certain with a 95% chance to see 2 or more adverse reactions. Now, this is kind of like Bayes' theorem. And the reason I bring that up is it's one of those areas of probability. Now, this is not a statement about herbs or herbal medicine, nothing like that. This is just an example. But it's kind of like Bayes' theorem, where something doesn't seem right because it's counterintuitive. If the probability is 1 out of 1,000, then you would think that you would see 2 out of 2,000 and 3 out of 3,000 and so on and so forth, because that just mathematically would make sense. You double the number of people, you usually see double the number of reactions. And if this was purely math, that would make sense. But we're talking about probability and statistics here, where things start to get a little bit fuzzy. And it isn't a guaranteed. This 1 out of 1,000 that we have here doesn't guarantee that out of every 1,000 you will see 1. It just has on average that if you ran this thing, say, 10 million times, 1 out of every 1,000 of those 10 million, you'd see a reaction. Which is why the counterintuitiveness comes into play, that it takes about 4,800 patients, 4,800 people being run through this experiment before you have a really high chance of actually seeing 2 or more adverse reactions. And there's a less than 5% chance that this won't happen. All right, so that brings us to the end of section 8.4, which is binomial probability. In section 8.5, we're going to take a look at some expected values and probability distribution. We're going to kind of tie this all up and make it, try to make it make sense in terms of how this would apply to like in a business sense or in an application, why we study probability theory. So I'll see you all back here for that one.